Okay, you guys, so we are going to have you fill in some notes today, and it's going to feel weird and very different type of talk, but please realize that whenever we see you guys in person, after we're done with the oxygen lab, we're going to be going through this in a lot of detail. You're going to get to see some models and really start to grasp what's going on. Probably the biggest thing to also remember is, as we've been talking about the electrons, Bohr and even Rutherford, they both thought the electrons circled in orbits around the nucleus. Remember, Miss Merkus showed you a little bit of a video showing that they actually have really, really strange shapes of what these regions are where the electrons are found. Unfortunately, those regions are named orbitals. So when I hear orbital, I go back to and I start thinking, oh yeah, it's going to orbit the nucleus. Orbital just means region. And what it is a probability region of where we're going to find these electrons. So we have to get structure and order to how to name these regions. And you're going to see us do that with lettering and then also with numbering, because we wanted to give a way, it's almost, think of it as like a Morse code as to designate how far away from the nucleus these specific electrons, when they're in their ground state, whenever they're not being given energy of electricity or heat, where we are most likely, it's a probability chart of where we're most likely to find exact electrons. Okay, so think from that point of view. So I think Ms. Merkus kind of took you through, I believe, this part of your notes. So we are looking at, I think this is page 6 in your notes, but just the next part. And some just terminology to catch. So with the wave mechanical model, which is just the modern atomic theory, it ended up giving us detailed information regarding these few things. First of all, something that's called principal energy levels. It's going to give us information about that. It's going to give us information about the different sublevels that are allowed in each energy level. And it's going to give us information about the shape of these probability regions. So those can either be called electron clouds or orbitals. I prefer electron clouds because then it gets my brain away from thinking an electron circling the nucleus. It's not. Remember, it's jumping around. So UW-Madison Badger fan jumps around. It's like a lightning bug. It lights up once in one area, and I can just guess where I might see that lightning bug light up again in a room, but I do not know its path in between the 2 points where it lit up. So think like that, like it is an unpredicted movement of that electron. We can just tell you where we think we're going to find it. So if I see a lightning bug lighting up inside my classroom, I probably will not pick out in the hallway to be the next place that I see that lightning bug light up. I'm going to pick some other place within my classroom that I'm going to see that lightning bug light up. That's what these regions are. They're probability regions of where we find these electrons. Okay. So it's going to tell us the total number of electrons that can exist at each energy level, sublevel, and also in the electron cloud. Now, theoretically, we could have an infinite possibility of principal energy levels, but we're only going to concern ourselves with the first 7 energy levels and the first 4 sublevels, because this knowledge covers all the known elements of the universe at this point. Okay, so here we begin with just, kind of strange talking. Today, we're going to be filling in the notes. Whenever you come back in person, we're going to work with models. You're going to get to talk to me. We're going to do a lot of practicing of what the heck this means. So the very first energy level, the very lowest of all electron levels, the closest to the nucleus, is given the sublevel S. The number of electron clouds that occur in that sublevel is 1. And the total number of electrons per sublevel, remember each sublevel we're going to learn can hold a max of 2 electrons. So the total number we can have is 2, because I'm just doing 1 times 2. And the total number of electrons allowed per energy level then is also 2. So the S probability region is sphere-shaped, okay, hence S. Energy level 2 has 2 different sublevels that are, this would relate, like if you think of the period on the periodic table, so going left to right, the rows and periods, this would relate to the very first period, so hydrogen and helium. There's a reason there's only 2 elements written up there. Okay, the second energy level can hold 2 different sublevels. It can hold S, which is going to be repetitive from up above. You know, there's one, the number of electron clouds that occur in that sublevel is 1. Total number of electrons per sublevel is 2, but it has now this new probability region that they designated with the letter P. So sublevels are designated with letters. Energy levels are designated with numbers. Okay, so sublevel P. P has 3 different probability regions. And if you look down here below, you can see that. Okay, my cursor just made it cover up. But these are the 3 different probability regions right here. They combine together to make this kind of XYZ looking dumbbell thing. Each region, so like this green would be one probability region, this yellow could represent another, and then the purple could represent a third. Each one of those regions can hold a max of 2 electrons each time. Okay, so 2, 2, and 2 to give you a total of 6 electrons in that region. Now, when I first was learning about this, I thought in my brain, oh, that means there's like 1 electron, you know, cute little electron over here in this purple, and then there's another cute little electron over here. It might not be like that. They might both be right beside each other, but it can't hold more than 2. Purple can only hold 2 at the most. Yellow can only hold 2 at the most. Green can only hold 2 at the most. So altogether, the P sublevel can only hold 6 at the most. Okay, again, if I go back up here with the S can only hold, each sublevel can only hold 2 electrons at the most. So, you know, here's the sublevel S. There's only one shape, 2 electrons. But here you've got an X, Y, and Z axis. Okay, so that's why, and each sublevel can hold 2 electrons. So 2 times 3 different options gives you 6 for a total of 8 in the second energy level. Okay, so the P sublevel is dumbbell shape. And if you look at the second row of the periodic table, and if you were to count how many elements are there, check that out. You've got 8 elements, right? Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. 8 different elements. Now it gets a little wonky with the periodic table starting with the third energy level because, of course, things can't always be amazingly clean, tidy, and wonderfully neat. But we will be discussing, because you would go, oh, well, the third energy level must only have S and P's allowed as well, right? Because I look at the third period going across the periodic table, it also has just 8 elements. So, you know, maybe if I'm catching this pattern and I go, okay, well, yeah, it must just be S and P's again. But as our energy level increases, you're going to see we can always add another sublevel. There's going to be a new letter that's added. So here we go. What's the new letter? Well, we're going to have repeats of what we've already learned. There's still an S in there. Just now just a little bit bigger. Third energy level, 3S, a bigger sphere. Okay. S's can only hold 1. They only have 1 electron cloud. They can hold 2 electrons max. We have another P that's a little bit bigger dumbbell shape, bigger than the 2 P's. Okay. That's kind of like on the outside. Think, you know, if you go back to the S's, think like the 1S would be the egg yolk inside a hard-boiled egg, and then the 2S would be like the white on the outside of the egg. Okay, so think like that they're both spherical shape, kind of. They're just getting bigger and further away from the nucleus. Same thing with the dumbbells. The 2 P's are smaller dumbbells, and the 3 P's are a bigger dumbbell that engulfs kind of the 2 P's within it. Okay, and these are probability regions of where we find electrons. Probability regions of where we're going to find these electrons. So P is same like what we saw before. 3 sublevels. Each sublevel can hold 2 electrons total, or I'm sorry, each electron cloud can hold 2 electrons total for a total of 6. New letter, new energy level, we get to add a new letter. And look at the complicated shapes there. It gets really irritating. D. Now, if you think about what we've done, take a guess of what our number of electron clouds are. Look at the picture below. I see 1, 2, 3, 4, 5 separate strange little XYZ axes, all kinds of like, imagine Schrodinger coming up with this equation, you guys, that came up with these 3-dimensional probability regions. I mean, just I'm fascinated that there are people that smart in this world, and I'm thankful that there are people that smart in this world. So now if you smush all 5 of those separate drawings together, you see this strange little balloon thing going on over there on the right-hand side. Okay, so how many electron clouds do we have with D? 5. 5 separate probability, 3-dimensional probability regions of where we're going to find those 2 electrons. Okay, it does not mean, this is where Mindy Zielinski was screwed up. Well, at that point, it was Mindy Hickson before I was married. And I was sitting there in Texas A&M in my college class thinking I understood the electron and going, oh, yeah, well, sure. How in the world can 1 electron fit in each one of those 4 little dumbbell shapes? I thought we could only put 2 in each electron cloud. So I had it wrong. These are probability regions, you guys. It might show up in any one of those 4 sections. You know, if we were to look here, it could be any one of these 4 sections where I'm going to see 2 electrons. They might be side by side. They might be one up here and one here. But it's all the probability of them being in these spots, these 4 little dumbbells, is all the same. This is a different orientation. We've got another 2 electrons that can exist here. We've got another 2 electrons that can exist anywhere here. Oh, or a cute little donut area. Again, how did they come up with this math? It's phenomenal. Another 2 electrons, so this would be like 7, 8 electron, can fit here, anywhere, any of these 4, different orientation, and then electron 9 and 10 somewhere over here. So just, process what this means. It's phenomenal what this man came up with. So what's the total number of electrons that are allowed in this energy level? 18. Okay, so how does this relate? This would represent your, that shouldn't have said third. That should have said 4th period. Good job, Zielinski. So if you look at the 4th period going across with potassium, it kind of goes with the 3rd, and this is where, it gets kind of wonky here, but where you can really count out 18 elements, and we'll explain the wonkiness of it once you're in person, is look at potassium. If I count how many elements are in that 4th period, potassium, calcium, and then I keep going, I would count 18 electrons, 18 elements, I should say, all the way across. That really, you're going to see the connection between that and the fact that there's 18 electrons listed right there that we filled in, okay? 4th energy level. Okay, we've increased energy levels. What are we seeing as a trend? We get to add one more letter here, one more sublevel. So we still see S's that hold 1, 2 electrons max, P's 3, 6 electrons max, D's 5, 10 electrons max. You guys are going to have to push pause to catch up. Sorry. F. Okay, you can't see any of this because all my junk, that stuff is in the way down there. And I don't know how to help you with that. And it doesn't help whenever I touch things. But you can see it on your handout. 7 different probability regions when they're all smushed together. That strange, looks like a COVID virus or something. But with that thing all the way to the right, okay? So 7 different probability areas of where the 2 electrons in that region might show up, or more likely to show up. So 7 different shapes all smushed together in that far picture on the right. And if I can have 2 electrons in each of those different orbital predictors, those different probability regions, that gives me 14 total. Okay, so how do we equate this? Altogether, we have 32 electrons. I wish I had a periodic table. Pause out. Hold on. Let's see how easy or hard this would be. Let's see if we can find a halfway decent periodic table. Because this gets into our lanthanide and our actinide series and how that fits in. So if you have your periodic table in front of you, I'm just trying to see if I can find one here that would be halfway decent. Maybe right here. Let's see. I can't read very well. So, oh my. We're on the Ducksters site. All right, so if we look here, this will work pretty good. We already were counting, the 4th, the 5th, even the 6th, we're thinking. And we go across and we count 18 electrons, or 18 elements, I keep saying, but that's going to equate to 18 electrons. Now, we just came up with the number 32, right? Where does that come from? Okay, don't forget that right here, these elements are really supposed to be smushed up into and in between 57 and 72 here. In fact, let's do periodic table, I don't even know, elongated? Oh, look at that. Someone knew my words. Okay, this will be a good one. So now when we look down here, oh my goodness, look at all these amazing periodic tables. Where's the long one? This one. So now we're down here where cesium was. Okay, if we go back up here, this was period 4, this is period 5. Look at this. If you were to count all the way across with these elements, take a guess. How many boxes would you find? I hope you're saying 32 in your head or out loud right now. Why? Because we now have these extra 14. Oh, I wonder what these will end up being. We're going to learn that these are going to represent those F orbitals. Okay, so the periodic table literally is a roadmap to help us with where these electrons are located, right? Things you did not know when you're in freshman science. So if we go back to this, again, like how I showed you, it kind of begins with the third period with the third energy level here, and same thing with the fourth energy level. We'll see how it begins with the fourth period, but we might not, and we'll talk about why we don't actually see it showing up until we get down to the lanthanide and the actinide series, or we get down to the fourth row whenever we start talking about like scandium through zinc and things like that. Okay. All right. I'm going to see if I can, I wonder, oh, it'd be really nice if I could mute. I think you guys are going to have to just listen to really weird sounds as this comes across. Sorry. I'm sure one of you could teach me how to do this. Okay, so this is the S one. And again, we're trying, pretend like right there at the axes, at the origin, is where the nucleus is. So here comes in the P's. So, and I don't know if this is going to have us go like, 1s, and then I don't think it did like 2s next, but this just shows you what those p orbitals look like. And then I think that this one's going to show you what those d orbitals look like. So remember, there's 5 different probability shapes with the d orbitals. So there's the second orientation, and we're going to see a 3, 4, and 5. That's my favorite one because it reminds me of a donut. So that, it's, okay, so now here comes in, I wonder what they're, sorry, now I'm feeling lost. Maybe they're just trying to show, oh, they're trying to show it to you all at the same time. So that's what Bohr should have come up with whenever he was thinking of what the electrons did instead of what. Now I like this one because I think this one also like it shows you the energy level. So what would 1s look like, and then 2s goes on top of that, 2p, 3s, and then 3p. So let's take a look at. Oh, well, Zelensky, you can't do it like that. If I push play, does that work? There we go. Okay. So here's 1s. This would be the simplest of all levels, right by the nucleus. Here's 2s. Holy cow, it goes quick. Oh my gosh, Zelensky. I'm going to try this again. I wonder, hold on, people. I know you guys probably love when I make a video because I'm just like, I'm all over the place. Sorry. I would not be a good ab liver. I want to watch this in YouTube so I can pause it out. Okay, so here's 1s. So this would be, again, the simplest of what we have seen. So 1s is coming in, and now the second energy level, remember, can hold s's and p's. So it's going to fill in on top of 1s. So here we go. Let's watch 2s come in. There's 2s coming in. So now we're in the second energy level. They're trying to show that to you up here that I've just covered up. And remember, the second energy level can hold s's that are spheres and those dumbbell looking things. So let's watch those 2p's coming in. So here comes the 2p's. So now we've shown 2s, 2p. Now we're about to show, and see how 3s is even bigger? So it's engulfing all of the 1s's, the 2s's, the 2p's. It's engulfing all of those. Here's 3s. And remember, that third energy level can hold s's, p's, and d's, but I think this one is only going to show you up until 3p. So our p's are going to go back to being dumbbell shape, and see how they're just a little bit bigger further out than the s's. So here's the 3s that's in here. Here's the 3p, and look how, that kind of engulfed, if you think about it, they're still trying to show you the 2p's that are within that. The 2s would be even within that, and the 1s we can't even see anymore, but it's there. Okay? Why is this so long? I wonder if it shows us more. Let's keep watching. Ooh, now it rotates. What fun. So see how you can see those p's that are within. So the 2p's are hidden within there. The 2s's, like there's the 2s that's in there. Oh, I guess I can see if I look real carefully, there's like the 1s right there. Okay. So these are probability regions of where we're going to find these electrons that, let's think about, go back to what you learned with the light. So let's say that we had an electron right here for copper that likes to hang out in this 1s, in this inner circle spot. We gave it energy, electricity, whatever it might be, and it jumped to here maybe. Maybe it jumped to a 3p region, and it's supposed to be in the 1s spot. So it jumps to here, and to get back home to that 1s spot, it has to give off light in the green light, whatever it might be, but get off energy in the form of light to get back to 1s. So, Bohr wasn't that wrong. He just had the shapes wrong. And he had the fact that it orbited and circled the nucleus wrong. So that's, I guess to an atomicist, that's significantly wrong. But he had the right idea, and that the electron gets energy, it jumps away. And to get back to ground state, it gives off energy in the form of light to get back to where it was. Okay, let's see what else is going on here. Oh, it's going to give us 4s. How exciting. Okay, so 4s is even bigger. See how it surrounds the 3p's? Oh my goodness, look, it's even so amazing. It's giving us all these 3Ds. This is getting, imagine if Bohr came up with this, you guys. They probably would have been, they'd have sent him to jail. Sorry, what do you think the electron's doing? So see how within this, whoever made this computer model, nice job, because you can see all of those hidden within electron cloud. I've always thought how cool it'd be to do this with balloons somehow, but I don't know how you would do it. So we got a feel for up to 3Ds. I wouldn't even know, it would be, do they have a computer model to show what the Fs would look like? I've never even seen someone try, I can't even buy models of the F. We can just see pictures of them. So, we have here at school some models that you can look at of S's and P's and even D models, but I've never even seen F models. Doesn't mean they don't exist. I'm just saying that I haven't seen them. All right. Okay, so that video kind of showed that, but how does 1s compare to 2s, compare to 3s, so on and so forth? So the electron clouds that are closest to the nucleus are the smallest and have the least amount of energy. The orbitals that are farthest from the nucleus are largest and have the most amount of energy. Okay, so, and we saw that with that video. Here's just another picture example. So the 1s, much smaller. If you imagine the origin to be where the nucleus is, so where X and Y and Z all meet, that is the nucleus. 1s is a little smaller, 2s a little bigger, 3s is the biggest. So larger energy level, larger size, further away from the nucleus. Takes more energy, if nucleus is home, takes more energy to get away from home. Okay. And then we can see this here. So the blue in this picture would represent the lowest energy, so it would represent 1s. And then the red circle a little bit further out and totally engulfs the blue, that would be like the 2s, so that's a middle amount of energy. And then the P's are even further out than that, and that would represent the most amount of energy. Okay, so just another way to look at it here. Okay, I think that is it. I stayed under 25 minutes. The at-home people, have fun, and we'll see you in school very soon. You guys take care.